Hello, my name is Eugene Miyao. I'm a vegetable crop advisor with the University of California Cooperative Extension. I'm located in the lower Sacramento Valley in the Woodland office, and I'm covering Yolo, Solano, and Sacramento counties. Today I'm going to be talking about irrigation management of processing tomatoes under drouthy conditions. I'm gathering information from a number of my colleagues, all of them whom could be doing a far superior job than myself, and these are presentations that I've gleaned information from. If we looked at canning tomato production, it's primarily and almost exclusively grown in the Central Valley, from Colusa to the north to Kern County to the extreme south. There's a little bit of production in the central coastal area. So this is an image of production practices that I describe when talking to a general audience. And once a field is selected, then the factors become these main ones. Variety selection has been very important. It's increased our processing tomato production over the years in a fairly dramatic fashion. Nutrient management important, controlling all these various pests. And then irrigation management has been very critical. Critical back in the day, critical certainly today. And under furrow irrigation systems, the irrigation management really decided what higher yields were compared to sub-yields. So if we looked at critical plant growth stages, the times to avoid drought stressing or moisture stressing the plants are during this flower period, the flower setting period, as well as looking at early fruit sizing. We can see flower set being critical because we don't want to be dropping those flowers, losing production, as well as during early fruit sizing, you can limit the potential growth of that size of the fruit, as well as under extreme conditions create blossom end rot. If we look at irrigation management, and this is a scene of a furrow irrigated field, if we look at changes sort of historically, one of the big changes was mechanized harvesting of tomatoes, a once-over destructive harvest. What happened in the early 60s when mechanical harvesting was introduced, there was great cultural practice changes with tomato production. One of the very obvious things at the time of harvest was bringing in this heavy equipment that fields that were irrigated late into the plant growth stage, that it would create muddy field conditions, these harvesters would get stuck, and so irrigation management became an issue of cutting off early enough to get this harvest equipment into the field while maintaining high production. And during that process of early irrigation cutoff to prepare for harvest, it was noted, and then research followed, that soluble solids increased with this moisture stress. While yields were curtailed a bit, the greater that moisture stress that was imposed, soluble solids, fruit sugars increased. So there's that inverse relationship between yields and fruit sugars. And that becomes a manipulation point for processing tomato production. So if we look at the crop coefficients, we see that the crop coefficient, it builds up, it maximizes at about 110% of reference ET, and a critical time in terms of irrigation management, if you're going to stress the plant, it's during this fruit ripening period, about 30 days, 40 days, 45 days before the intended harvest time period. So that's sort of it in a nutshell. So now let's look at some of the details. This is a presentation made by one of the irrigation specialists, Blaine Hansen, along with a colleague, a longtime farm advisor, Don May, working in Fresno County. They work together to collaborate on some of this information. So overall, how much water is required to grow this crop? 21 inches, to 30 inches, quite a range. But as you look at this graph, you see that 21 inches or so, it's at kind of early maturing varieties, short season varieties. And then the water requirement goes up as these harvest is into the longer maturing varieties, longer to ripen. And we have a number of early maturing varieties as well as kind of late maturing varieties. And so we can see water usage increases with the longer that season occurs. So perhaps a long-term strategy might be for plant breeders to look more at developing high-yield, earlier maturing varieties. That could be a strategy if we're locked into a long-term drouthy situation. The problem with some of the plant breeding, though, is that our early maturing varieties tend to be lower yielding. Now here's a graph that's interesting should be to many of us, is that if we look at California production, average statewide yields, that yields have gone up almost linearly from the 70s and the 60s through the current time period. And this graph ends up in 2004, but if we continued it on, current yields are approaching 50-ton average yields per acre. But the good news is that while yields have gone up, the water requirement for the crop has remained fairly stable. So to increase production didn't mean an increased need for more water for the crop. And it should be noted that in terms of this crop coefficient, you need to be paying attention to canopy cover as relating to this crop coefficient. So again, we said that it maximizes at about 1.1 compared to the reference ET. Now, can we take advantage of seasonal plantings? For the processing tomato industry, unfortunately, that it's a long planting and harvest window. The processors want to harvest over an extended time period. So while it might be more advantageous in terms of short water years to plant early in the season, let's say March 1st, and harvest sometime into July, as we see here, this March planting, that the crop coefficient, water usage, is slow to develop as compared to during a hotter time of the year when temperatures are higher, that in this case in June, we see that the crop coefficient goes up quickly and rather dramatically. But if we were in extended drought period, I would think that many processors would want to increase their processing capacity to take advantage of limited water supply and trying to get as many tomatoes in as possible with that limited water supply. But right now, shifting to only plant early season may not be possible. But for individual growers, perhaps contracts early in the season might be able to then extend the water supply with that limited availability. So that might be a strategy for individual growers. If we looked at this chart, we see that if you were water stressing throughout the season, in terms of evapotranspiration, if you cut back on evapotranspiration, you're cutting back on yield. And it's almost a linear relationship. Reduce water supply, reduce yields. This is a chart from Don May, a farm advisor working over several years. He was working with drip irrigation, a rather severe cutoff 60 days before harvest. And we see the different varying amounts of applied water in that 60-day period close to as it approached harvest. That we see, I think, two things. The primary things I want to point out is that on clay loam soils, when you reduce the water, the impact was not as great as on sandy loam soils. In part, probably the reason for that is that there was stored water, more stored water in these clay loam soils compared to the sandy soils. The other thing to note is that it was only a few inches, in this case 2.5 inches, when they said we applied only 50% of evapotranspiration. You see that on the clay loam soils that they suffered maybe a 10% yield reduction. So it would vary, however. We need to caution growers that it all depends on the soil type, the soil situation, how much stored water was there and available prior to this cutoff. So now looking at trying to stretch this limited water supply, well, what are some of the tactics? Drip irrigation certainly has been very attractive to most growers because of ability to more precisely apply the water. Comparing that to furrow irrigation, where there's can be considerable losses. Surface runoff, deep percolation are problems associated with this furrow irrigation system. And we'll talk a little bit more about that. So, in furrow irrigation system, what are some of the strategies? Perhaps cutting this row length down so that the run length is shorter, more control of the water. And if we look at this particular chart, if water was, the inflow of water was on the left-hand side in this little graph, and this is the inflow of water, and the magenta colored area is the water infiltration. We see as the water advances that we see that wherever the water was associated the longest time period has the most deep percolation, and at this point water is running off the field. So in order to get water infiltrated down to the root zone as water is leaving the field, you need to continue to have this runoff, and that becomes the problem. So how to try to get more efficient? Shorten the irrigation run, perhaps reduce the flow once the water reaches the end of the field, so you have less runoff and still have water running to try to increase percolation in this area of that irrigation run. So what are some alternatives? Perhaps it's every other row irrigation, as demonstrated by Louise Jackson and Felipe Barrios. What they believe they saw is this: when they measured the number of fields, and these are commercial fields, that yield stayed relatively the same, not statistically significantly different. But when you looked at these alternate furrow irrigations, as depicted by the green bars, we see that water savings was associated with the alternate furrow irrigation system. Now, was that captured by efficiency of the irrigation system? Did it change some transpirational sort of physiology of the plant? It's a little unclear, but there might be room to explore that further. Now, let's look at drip irrigation and irrigation scheduling. This is information that has been developed or compiled by Tim Hartz and Blaine Hansen. It's available on a website, and it gives kind of a recipe for irrigation scheduling. Basically, it's covering reference evapotranspiration and looking at the environmental conditions as well as plant size. And we talked about looking at plant size as adjusting for the crop coefficient. And that's very important to do and adjust it during the season to be irrigation efficient. Other things to check for, though, kind of simplistically, would be that while you may be setting irrigation run time with a drip system, it's also important as a check to look at irrigation flow, using flow meters on the main lines, as well as perhaps some on the individual drip lines to check to see if volume of water is really being applied as the hours of runtime say they are. And we can see that pumping capacity might change over the season, especially with deep wells and such. Soil moisture sensors are important. So placing a moisture sensor somewhere near the drip tape at maybe slightly below it, as well as a probe, a moisture sensor that is much deeper, so that you might be able to detect whether you're over irrigating because the sensor never moves away from being completely wet, or if you're deficit irrigation and you're seeing drier and drier soils as you think you're irrigating efficiently, you know you need to adjust. So moisture sensing is important. Finally, talking about managing end of the season irrigation, we're repeating this, but here's a crop coefficient. And we see that during the fruit ripening period, that is the stage where deficit irrigating will have the least impact on yield. So that should be a target area. How much to deficit irrigate depends. So it depends on how much stored moisture is in the soil before you begin this deficit irrigating at the early fruit ripening stage. Also, if it is a soluble solids, fruit quality management scenario, knowing how much you might want to increase those soluble solids. What else? Well, what else? Can we change tillage practices? Might we, in this case, we're looking at a small grain planting directly into a harvested wheat. Could we do the same thing with tomato production? There's been some research attempts at doing that, and some fairly successfully, but it still remains a challenge. Can we then minimally till the soil rather than broadcast deep tilling? Can we retain the bed shape and just surface till these soils? And there's movement in that direction. So what about trying to capture winter rainfall and retain it on these fields so that in the springtime, when these soils dry a bit, that there can be very shallow tillage rather than deep tillage to try to, in this case, retain soil moisture? What happens with the benefits of cover cropping off-season? We think that in drouthy years is going to go away because we cannot afford to these plants to dry the soil moisture. We want to retain it and bank that soil moisture. So unfortunately, we believe that cover cropping might be a casualty of this drought period. And not only does a cover crop take moisture, but then the tillage practices behind this to get the seedbed back into condition means further soil drying. So that's a problem. Direct field seeding. Probably not going to, there's going to be less direct field seeding in the future as well. And one of the problems is that planting that small tomato seed directly in the field oftentimes mean having to continue to irrigate to germinate the crop. And it could be multiple irrigations to establish a stand with direct field seeding. This is why the industry has moved largely to using greenhouse-grown transplants, having these plugs grown efficiently in the greenhouse, taking these plants out into the field, and directly then placing these into the field almost like an instant stand. And so that industry has converted almost from zero in 1990 up to now to be exceeding 95% of the industry is converted to using these transplants. Why the switch in 1990 or so? Water shortage was one of the primary reasons for moving to transplants. There were other reasons, but water shortage really was one of the drivers. Sprinkler irrigation, we believe there's continued to have some sprinklers used, especially for establishing these young plants ahead of either drip irrigation or furrow irrigation. We're going to see, I think, into the future, even less furrow irrigation on tomato production, given a limited irrigation supply or water supply. Drip irrigation has become very popular, and not a surface drip, but a berry drip system. And we've seen that this is somewhat of a tracking over the years. So by the year 2000, certainly there's been a large movement of the California canning tomato industry towards the use of a berry drip irrigation system. Irrigation efficiency was a driver, but also yield increases have resulted from the more precise management of this irrigation. We talk about pest control. And that still remains important. Weeds, as one of the pests, then take moisture away from the crop. So controlling weeds and that unwanted vegetation remains important. But also these other pests, such as insects, that reduce yields. Because we're trying to capture the highest yields given that limited water supply. So pest management remains an important driver. We hope we see continued water deliveries from surface systems. We know that we're seeing much more use of wells, a lot of wells being drilled in our valley under these drouthy conditions, but there's clearly has to be a limited underground water supply. So we're concerned about that. These wells are going deeper. Growers are drilling deeper for that moisture, and so we need to be careful with that even. And we know that we can't grow very many crops without water in our valley. So with that, I think we're concluding. We hope that when we talk about wishing a lot more rainfall, we know that it's a time issue. So we hope we still have Mediterranean conditions in our valley, just so we have a lot more rainfall and snow during our off season. So hopefully that's addressed some of the questions. There probably are others that have been raised, but thank you very much for opportunity to speak with you today.